Thank you. Okay, hello everyone. Welcome to the second class. I would like to start with one general remark because I got quite a few emails asking me a bit about what kind of level the course will be, if it's like purely applied or purely like mathematical. And like at the very beginning of last course, I asked you, okay, to raise your hands if you're like engineers and raise your hand if you're mathematician. And it looked like part of that class was mathematician and half of them were engineers. So it's a bit of a challenge also to me to give a course that has like so many different kind of backgrounds. So what I try to do in this course is to balance that. Like it will be slightly different for the people that are used to really mathematical lectures, and it will be slightly different to the people that never had like a mathematical lecture. So what I try to do, for example, is like give like the proper background and like the proper definitions, and also include, for example, assumptions like smoothness in the definition of like my objects that I look at. But sometimes I'm a bit like hand-wavy, and I will not describe like too much into detail how to solve certain problems or verify that all assumptions are verified. So I try to make a balance between like that, like the people that would like to know the proper definition, like have the material, and at the same time also the people that don't care about the definition but just want to calculate certain things also have the tools to do that. So there will be a bit of uncomfortableness for both of you. There will be a bit of too much hand-waving for mathematical oriented and a bit too much mathematical knowledge for the people that never have had a class like that. So just like give yourself also maybe some space to be feeling uncomfortable with like, okay, that's slightly different than what I used to, so it's totally fine. Just like experience that and like try to learn to deal with the uncomfortableness and like, for example, look up certain definitions that you have not used to, or like accept that certain things are not as strictly defined and look up how to do that more rigorously if you're really interested in that. So just like as a general remark, I try to balance both sides so that all of you have like something to take away. That about like the general thing. If you have any questions, come afterwards after the class to me, and then we can discuss that also a little bit more. Okay, let's start with the more interesting part, namely the Frenet-Serre frame that we discussed last time. So remember, we had our curve, and it was very natural to look at the first derivative of the curve, which would be like the tangent vector, and then orthogonal to that, as we saw, there was always the second derivative, and they're indeed orthogonal once we assume that our curves are unit speed curves, which we are always able to. And then up to normalization, this one is denoted by t, and this one is up to normalization denoted by n. So these are the two vectors that we have. If you ask AI to draw you a picture of the Frenet-Serre frame, then you get something like that, which is completely bullshit. So you already know more than AI, but it looks nice. So that's like the proper Frenet-Serre frame. It's like at each point you have like a tangent vector and something that is normal to that. I would like to discuss some applications to really give you like some idea of why you should look at these things, even if you're completely applied to. And for that, assume that we drive like a car, or like we want to like model that and like have like a self-driving car, for example, that like has some objectives and wants to drive around that, for example. And so what you have like intuitively how you would model that is like you have the middle point of the road, and then your car is moving on the road. So like what you have is that it looks like that you have the barriers of the road, which is giving you two different curves, and like the objective is to have your car always driving on the road. So that would be like your objective, and you need to control the speed of the car, for example, on the steering. So that's how you would intuitively set that up, right? Like that's like very intuitive what you would do, because like the roads are something that you get from like data. But what happens now is that if you rephrase this problem and instead look at a Frenet frame where you take the middle line of the road, say, as like the curve that you take as a reference for the Frenet frame, then what happens is that you transform this curved line in this Frenet frame. It's just like a straight line. And what happens then that like these barriers that you like the sides of the road are also then just transferred to something that looks almost straight, or like in the ideal case it's just like two straight lines. So what is like now happening is that you have like a nonlinear problem here where you have to balance like how much you steer towards like a completely linear problem where you have just two lines and you have to stay between two parallel lines, which is like way easier. So by just knowing like that there is like a nice frame that can be seen and that is adapted to how the curve looks, you can transform like a really complicated problem, like driving on a road, into something that is very easy, namely just like staying in parallel lines. So that's an application. What do you think is like the problem with that approach? like what kind of problems would you like think about if you say like, why would it maybe be more advantageous to look at this instead of this formulation? What kind of problems do you can imagine with the second one? Just raise your hands and. So for example, what happens if you describe your car like being in relative to this frame where you just like say like how much distance you have, say, to the normal direction? What is like the problem with that? Like one problem is that in this description, for example, the car, like if you want to know its absolute velocity, because you need to say like the car needs to drive less than a certain velocity on the car, there's usually some restrictions there. It's very hard to do that, or like relatively hard to do that in this René frame, because it's relatively to this kind of like normal line in the middle. So like the velocity is not an absolute velocity. That's not the real velocity that you measure, but it's the velocity relative to a different coordinate system. So in order to like impose speed limits, for example, you have to recalculate that what the speed limit means in this kind of like frame. So that's one of the problems. Another problem is that things that like were originally nice and square in your original frame now get distorted because like you measure essentially things that are like distance-wise to like a curved, like you measure distances relative to a curve. So that things that like the car, for example, is actually not like a square box anymore, but it's like just distorted. So that's like some problems. And sometimes what like in practice why it's I think usually not used is also that you, for example, if you have two multiple cars and you need to coordinate how they drive, then they are like in different kind of frames so that it's like sometimes hard to compare where they are. But yeah, like in principle, it's a valuable approach or valuable in some cases. And to show you how that looks like in reality, here's like the track of the car really moving on the road, and here it's the same depiction of the car, but in the René serial frame. And you can see like things like here that are getting distorted because the curve is so that's really a car trying to predict where it should drive and how it should steer to circumvent obstacles. So that's like one application is like transferring problems that are non-linear into something that is like nicer and linear in the René serial frame. So that's like something that you already know in engineering is that like certain coordinates are always nice to work with, and sometimes they make like your problem very easy, and sometimes they make it hard. Like polar coordinates. Sometimes it's really nice to describe a problem in polar coordinates. Sometimes it just makes like the formula super ugly. And it's similar here. It's like if you have like a curve and you want to describe certain behavior around that curve, it's usually very nice and very intuitive to work with the René serial frame instead of with like an external coordinate system. That just as a general application or general remark to that. Okay. I would like to give you some different kind of definition of curvature, or like some intuitive picture. Last time we defined essentially curvature as something in a kinematical way. It was the second derivative for the absolute value, the magnitude of the vector of the second derivative. So it's like was this picture of like you driving on some path, and like if you experience a lot of force that pushes you on the side, that means that you're driving through a tightly bent curve. That was like the intuitive version that underlined our definition last time. I would like to give like a little bit more of a geometric way that you really can see that as a bending of a curve. And for that, it's nice to approximate, or like to think of that as like the derivation from being like not straight. Like you look at like the straight approximation, and then you think, okay, like how do I measure that I'm not straight? And that the idea is to use something that is called an oscillating circle, which measures not like how much you're straight, but how like the second derivative, like how close you are to its ideal circle. So that's the idea, is to use this, to look at higher approximation. So the first order is just a tangent line. And the second order, I will discuss now, is what is called the oscillating circle. So the idea is that you have your curve, and you look at like a certain point, and then the first approximation of the first approximation of the curve is of course just a line that is tangent to the curve at that point. And the idea is to find like a second order approximation, which would be a circle which goes around, which touches exactly the curve there, and which has like a nice behavior that it's like really touching the curve in a nice way. That's the curve here. And osculating is just like a Greek word for kissing. So it's just like a circle that kisses the curve in some way. Like it's very close to that. So what do we mean by that? Is that we can look at like a curve, which is the circle, and which has like certain properties, namely that at 0, say that it's exactly the same value as the curve, and then you want like the first derivative is the same thing, and the second derivative at 0 also like to be the same thing as that. And as a side remark, like we want at C and also this one, which is also just a curve, are unit speeds. So if you have a curve like that, then it's called an oscillating circle. So like we really have like a second order approximation. The first approximation would be just a tangent line, and then now we have like more information that it's the second order. And in the homework, I asked you to prove that if the curve is regular and like the second derivative is non-vanishing, then we always have an oscillating circle at that point. So that's like an important result. Which was one of your homework problems, is that this one is not vanishing at that point, then exists a unique the idea is basically that the curvature of that circle, of the red circle, has to be the same thing as the circle, the curvature of the curve at that point. Maybe we call that here is that the curvature of this oscillating circle, sigma here, at 0, which, because the derivatives coincide to the second order, is the same thing as the curvature of C at the time instant t0. But we also know that the curvature of the circle is the same thing as 1 over the radius of the circle. So 1 over the radius is the curvature of the circle, and that one has to be the same thing as the curvature of C, and so we denoted that last time with kappa. So what we get from this kind of argument is that like, the curvature of that circle is proportional or inversely proportional to the curvature. So we get a nice relationship between the curvature of the circle and the curvature of the radius. So that means also that we can also see in the picture very nicely. For example, if you draw the ellipse, that's my original curve, and I would like to draw two different oscillating circles. One would be, for example, here, would be a kind of a nice approximation to second order. But if I'm up here, where it's almost like smooth, the approximation would be something like that looks like a really huge circle. Because it's relatively flat, the ellipse. So you see already that like you can measure like very intuitively from the radius of the circle, you see how flat the curve is. If the radius is really large, then your curve looks relatively flat at that point. So that's like exactly that the radius of the oscillating curvature is like inversely proportional to the curvature. So that gives you like a nice intuitive way to see what like the curvature is geometrically, and that it's really something that is like in line with how you would describe curvature as something like if it's like very round, then it has curvature, and if it's almost flat, it has low curvature. So that can be mathematically justified by this argument, because like what it means to be round is exactly measured by this circle that touches the curve in a very nice way. Okay, so that's that's all I wanted to say for that first part of the lecture about oscillating circles. But they will come back in a few minutes again because they're very helpful to study curves. But before that, I will we discuss a few more properties of curves and why they are nice or what kind of curves you can experience. And one obvious distinction between a curve is like something that has like an end, like this cable, for example, it has a beginning and an end. But like some of the curves don't have like an end. Some of them are like circles or they might be twisted, but they don't have like an obvious beginning and end. So there's like things that like these kind of things we call loops. So, and in the following, we would like to understand loops a little bit better, because they have like some quite interesting properties. So, loop. The curve, let's say it's parameterized to be defined as a unit interval, or more general, some curve, and we want that it starts and ends at the same point. So we see that the value at the beginning is the same thing at the end. And also we would like to see so all end, we want that like the value are the same and all the derivatives, saying that like the first derivative at the endpoint is the same thing, the second derivative, and so on for the second derivative as well. So what we would like to rule out is like certain things where we have like things like this, which is like a circle, but which has like this kink where the derivative at that point is like pointing in this direction, and the derivative at this point is pointing in that direction. So that's not like something nice because the derivatives are not agreeing. So we don't want this one. We want like something that looks like a nice, smooth, round curve in the loop. So that's what we understand as a loop. And of course, they might also be twisted and like has like some intersections like this. So that's also like a loop because it starts and ends at the same point. But sometimes it's nice to not look at things like this, and then we say that it's a simple loop. So that means that if you know what it is, that if you know what injective means, here's like a small remark what it means. Like what you don't want is that there's exists a point where we have like two times where the loop is at exactly that point. So we don't want self intersections. And then we call it simple. So this one is simple. And this one is because it intersects itself here at that point. Okay, so that's like just like some general remarks. And why do you care about simple curves? Is because if you look at this picture here, there is something like where you simple. Namely, you can say like the green tick that I draw is inside of the curve. Right? That's like very intuitive picture. That you have a curve like this, there exists something that you call inside, and there's something that is called outside. That's going to be harder if you have like an intersection like this, because would you call that inside or the outside of a curve? It's not clear, right? Like if you, it's like kind of inside because it goes around, but on the other hand, like it's also outside because like this curve, like in some way, like it's not totally clear what you mean by inside and outside there. So that's why simple curves are nice, and because they admit something that is like called inside and outside, and that's kind of clear for simple pictures like that. But if you can also imagine like you have like very complicated curves, right? So something like that, like where's the inside and where's the outside of that. So it can be pretty complicated to realize what is inside and outside, but there's a very strong theorem, which I will not prove, but which gives us a nice result that there's always an inside and an outside. And this one says that every simple loop So the theorem is nice because like it says two things. Like the first part is that we have like whenever complicated shape we can draw, we can always find like it always divides R2 into two sets. And one of them is like always enclosed in some really large ball, so it's like what is called bounded. So it doesn't go up to infinity. So that is what's called bounded. And one of them is unbounded, so it goes up to infinity. And when we say like that one, what is called is the bounded area, is what's called the inside of the curve. If you have a loop C, then that bounded area is the inside, and then the unbounded one is the outside. So in this picture here, this one is a simple loop, and then the inside is what you can imagine. It's this one. It's inside. And everything else, like the rest of the blackboard, is the outside of the curve. So we always have that. Regardless of how complicated the curve gets, you can always find something that is inside and outside. And that might be very intuitively clear that you can always define something as the inside if you have like a nice loop. But just imagine that it's like already doesn't hold in 3 dimensions anymore. Like here, for example, I have now drawn you a simple curve. It's a very nice one, but what is the inside of that curve? right? Like the inside, like it's like there's not like it doesn't separate like R3 anymore into something that is inside of the curve and something that is outside of the curve. You can imagine, of course, something that is like plane and then like it's like you can call that like this membrane thing kind of as like the inside, but it's not clear because like you can move that. So it's like not really a clear notion of inside anymore. But in a plane, if you have it in a plane, and it's clear that this one is the inside and this one is the outside. So it's sometimes it's like these things that you take for granted, that like there is an inside and an outside, but sometimes you have to really prove things. And actually, proving this theorem is really hard. It's so hard that I will not show you the proof, because it will take quite some time. So it's a bit more complicated to actually like discuss why like you can divide such like simple things in inside and outside. But it will be very important for us that we can say that there is something called an inside of a curve. And one of the things that we will use it is in combination with the oscillating circle. And that might be a bit counterintuitive. So suppose we have a simple and also regular loop. We call that regular meant like that the derivative doesn't vanish at a point. So it's like that we had last time. So let's call it C. And suppose that we have the curvature is never 0 for all times. So for all times the curvature is not vanishing. What this means by this result that we had before means that like at every point we find a nice oscillating circle that approximates the curve. But the result that I would like to discuss now is then that exists a point or time t0 in this interval so that the oscillating circle at the curve at that point lies inside of the curve. So that's the result that I would like to discuss now, is that we know from the first assumption that we always have oscillating circles at every point, and the result is that we find one point where the circle or the oscillating circle is inside of the curve. So to give you an example again, what we had before was, if you look at the ellipsoid, then if you look at this point here, it has like a really huge oscillating circle. And actually, the oscillating circle goes up quite a bit, and it's definitely not lying inside of the curve. So this one like doesn't fit the bill. But then you had like seen here at this point, the oscillating circle is small enough, and this one is inside of the curve. So we would like to find such an oscillating circle, which is like fitting inside of the curve that we look at. And from this picture, it seems you're already clear that not every point has such an oscillating circle. So at some point, we have like an oscillating circle which is like way too big and does not lay inside of the curve. But at some point, the claim is that we always find one point where this is possible. And this one is C of t is 0. So I would like to show you how to reason about this. And I think it's quite beautiful argument, but I don't want to make it super precise. So I will give some results to the literature. If you're really interested in it, then you can like read up like on the really concrete proof. I just want to give you some idea how to prove that and like what is the main geometric construction. So the main idea is that we use, or main construction maybe, is that we need something that is called a maximal circle. Which I denote by C of P at the point P. The largest circle that lies inside. So we want something that lies inside of the curve C. But we would like to have something, imagine we have our curve, and we choose like a point here, then this maximum circle, this one is the CP here, is the largest circle that we can like fit in our curve that fits inside the curve. And it's the largest one. So in this case, it touches the curve at some other point. Maybe if I choose here a different point, then we get like the maximal circle would be something like this. So that's the largest circle that fits inside there and has like the base point being shared with the point that we want. And it doesn't have to be it's just like one circle. It doesn't have to be the oscillating circle. So that's important. It's one circle that fits into the inside, but not like, it doesn't have to be like the oscillating circle. And the main idea is to kind of compare these kind of maximal circles to the oscillating circle and see what happens. got it here. An obvious result is that CP has to touch curve C at another point. So that you see from the picture is that like the maximum circle has to hit the curve at least at another point. It might actually hitting 2 points at the same time, but at least some other point, because otherwise if it's not yet touching this other point, then I increase slightly the radius until it then touches. So there has to be at least one other point where the curve, this maximum circle touches the curve. Okay. So now we would like to look at the proof of this fact here. So we would like to find such a point. So we don't really know any particular special point in the curve yet. So let's start with some, that we choose some point. Point P on the curve. So we choose like some random point. So maybe over here I draw kind of the picture, what happens. So we choose like a random point on the curve. So then there are two cases that happen. The first one, if the oscillating circle at P lies inside of the curve C, then we're lucky, then we're done, right? Like if the oscillating circle lies inside of the curve, then we are already finished finding our point. So that's like a bit of stupid. Then so if by chance we picked this point here, then we're finished. But like most likely we are not. We picked a point like here, where the oscillating circle is not inside. So this one is not. Then the radius of the maximum circle assuming that that the oscillating circle lies not inside of the curve, then the maximum circle has to be strictly smaller than an oscillating circle. So that in this picture, we draw that. the maximum. It would be the maximum circle. So that's the maximum circle that is inside of the curve, and the oscillating curvature circle would look maybe something like this, and then goes off to infinity, which has like a way larger radius than the blue one. So that's like the first step. It's like if we are not in the radius of the maximum circle, this blue thing has to be smaller than the oscillating circle. So that's the first observation. But what we saw also is that like this, the circle of the red thing, the oscillating circle is the best approximation of the curve. So it describes really well what happens of the curve near to the point. And what happens, like if you zoom in, what you see is that what happens then is that you have like a small circle, then you have the big oscillating circle, and then you have the curve, which is kind of going, looks like this. So that is kind of like the picture. And what that means is that because this blue circle has like strictly a smaller radius, we know that like in this curve, we can like, if you look like close enough to the point, it will never happen to intersect this blue circle again, because the best approximation is already the red circle, and that one is separating. So the radius of this one is bigger than this one. So the first point where the white line could very much be close to the red line, but it's never like if you make that interval small enough, like as round as like the blue one. So it will never intersecting the blue circle. So that's the next observation.